All right, in this example, we've got an RLC circuit attached to a current source that's got 24 milliamps. And in parallel with that current source is a switch that's been closed. So that current has just been shortened out forever. And then that switch opens at t equals 0. In parallel here, we've got a 25 nanofarad capacitor, a 25 millihenry inductor, and a 500 ohm resistor. And we want to find the voltage across the output terminals of this RLC circuit at t past 0, so t greater than or equal to 0. We're given the initial conditions for the current in the inductor, which is at 29 milliamps, and the voltage in the capacitor, which is at 50 volts. So let's go ahead and solve this using our Laplace transform technique. So first off, step 1 is always find the initial conditions. Now these are given to us, so we already know that the current, the initial current in the capacitor is equal to 29 milliamps, and then initial voltage in the capacitor is equal to 50 volts. Step 2, we need to convert our sources. Step number 2, sources. So we only have one source, this 24 milliamp current source. And when we convert a source into its S-domain equivalent, all we're going to do is say that the 24 milliamps, or I'm going to write it right here as 0.024 amps, just becomes 0.024 over S. And that's that. Step 3. Is all of the symbols, and from that all we care about is we're going to take our output V, which is a function of t, and we're going to convert it to capital V, which is a function of S. Step number 4, the circuit elements. All right, now the resistors will stay resistors, but we want to look at the capacitor and the inductor. So let's go ahead and take a peek at the capacitor first. Let's see, remember that our C is equal to, what was it, 25 nanofarads. And we want to change it to its equivalent representation in the S-domain. Now notice that we've got a current source in parallel with everything. And remember that we could do two versions. We could do the circuit element with the voltage source and the circuit element with a current source in parallel. And to make this a little bit easier, since we're already in parallel with the current source, we're actually going to stick to that. And we're going to go ahead and use the version of this that has the capacitor in series. Let me use a different color. The capacitor not in series, but in parallel with a current source. Now remember here, it's going to be the value of the current source is going to be C times V naught, and the value of the capacitor, or the impedance of the capacitor, is always 1 over SC. B and A. So let's say that 1 over SC is going to be 1 over S times 25 times 10 to the negative 9. And that's going to give us a Z of C equal to 40 times 10 to the 6 over S. And CV naught is going to equal 25 times 10 to the negative 9 times 50, which is going to get us a current there of, what are we going to have? Of 1.25 times 10 to the negative 6 So a really tiny current, 10 to the negative 6 amps. And that's ohms up there. So we'll go ahead and plug those in when the time comes. But first, let's go ahead and take a look at the inductor, which had 25 millihenries. Now, same deal. We're going to tack on a parallel, since there is a initial current. We'll go ahead and have the ZL. And remember, current flows with the inductor in parallel when you transform it. AB. And that's going to be equal to, let me double check my notes, I naught over S. All right, so let's go ahead and solve for those values. We'll get ZL is equal to S times L, which is equal to S times 25 times 10 to the negative 3 Oh, yeah, sorry. Kind of zoned out there for a second. That's equal to 0.025 times S, which we can actually simplify just a little bit to be S over 40. That's the part I was staring at my notes, like, how did we get S over 40? Yeah, 1 over 0.025. So S over 40 is our ZL, and then our I naught over S is going to be equal to, what was our I naught? Our I naught was 29 milliamps. So we'll just say 0.029 over S. So now we're ready to go ahead and actually draw the rest of our, or draw our new circuit here. So we've got our current source that was 0.024 amps over S. Now it's going to be in parallel with a capacitor that has 40 times 10 to the 6 over S ohms as its impedance. Now it's in parallel with that current source that has 1.25 times 10 to the negative 6 amps. And we're in parallel with an inductor that we found to be S over 40 ohms. That is in parallel with that current source flowing in the opposite direction. That had 0.029 over S amps. And all of that is still in parallel with that resistor still hanging out here, which is still just 500 ohms, and we're still interested in the voltage drop vis-a-vis S across those terminals. Whew, that was kind of a long one. All right, so what we want to do, since we have 3 current sources in parallel with 3 impedances in parallel, we can actually just simplify this circuit down to be just what we'll call I EQ in parallel with a ZEQ, and we're interested in the voltage drop across that. Now we know that our VS is just going to be equal to, let's use red, ZEQ times IEQ. So we just need to find what our IEQ and our ZEQ are. Let's do IEQ first. IEQ, equivalent current, is just going to be the sum of these currents. So 0.024 over S plus 1.25 times 10 to the negative 6 minus 0.029 over s which can simplify it down to be just 1.25 times 10 to the negative 6s minus 0.005 over s. Now our ZEQ is slightly more complex algebraically. Since our impedance is in parallel, we'll say that ZEQ is just equal to, we're going to flip all these over, s over 40 times 10 to the 6 plus 40 over s plus 1 over 500, and that itself is going to be flipped over. So when you do all of that algebra, you're going to get a simplified version of this that is 40 times 10 to the 6s over s squared plus 80,000 s plus 16 times 10 to the 8 ohms. Now we're ready to find our V sub s. So that's just equal to our IEQ, 125 times 10 to the negative 6s minus 0.005 over s times our ZEQ, 40 times 10 to the 6s over s squared plus 80,000 s plus 16 times 10 to the 8. And I'll leave it up to you to solve that, and from there we'll get a simplified version of our Vs, which is just equal to 50s minus 20 times 10 to the 4 over s squared plus 80,000 s plus 16 times 10 to the 8. We can actually simplify it slightly further and say that it's 50s minus 20 times 10 to the 4 over s plus 40,000 squared. So there is our value for s. Now we'll go ahead and skip over the check part. We'll go straight to the end here. We'll call it step 7. And that is just taking the inverse Laplace transform of our guy here. So if we take this, the first thing we need to do is break it out into its partial fraction expansion. Which, if you do that, you're going to get minus 2.2 times 10 to the 6 over s plus 40,000 squared plus 50 over s plus 40,000. And if you take the inverse Laplace transform of both of these guys separately, tie them together, you'll get that our final result, v of t, is equal to minus 2.2 times 10 to the 6th. It's s plus 40,000 squared, so it's t e to the minus 40,000 t plus 50e to the minus 40,000 t times u of t in volts. And there we go, there's our final answer. That one was a bit of a long one, so we won't do the check with initial and final value theorem, but you can go ahead and do it yourself to make sure that those answers are in fact square with each other, and they should be. So let's, yeah, I guess that is it for this one. As always, if you have any questions, comments, or concerns, please let me know. If not, I'll see you guys in the next lesson. Thank you.